All right, so the point of this video is basically go over the history of the modern table. That's the title of the PowerPoint. Basically, a couple key things is in the 19th century, chemists began to categorize the elements according to their similarities, either their chemical or physical properties. They started looking at them and started grouping them. Based on what happened over time, the end result eventually became the modern periodic table that you have, you know, and you love in your backpack and your chemistry book. So at the start, basically, you had our little buddy here, Johann, basically started categorizing or classifying elements by their properties into groups of three. They were referred to as triads because they're groups of three, and the triads all had similar chemical and physical properties. And if you notice in the modern day periodic table, they're actually in the groups together. So they started to notice similar chemical and physical properties in the early 1780 to 1849. Now, that was the idea of triads. So the idea of elements existing in groups of three. Then you had John Newlands in 1863 suggested that if you arrange the elements in octaves similar to the what you see in the musical scale, that certain properties did repeat every eighth element. He was kind of got a hard time. That became the law of octaves, very similar to what you see in music. The idea that there was a repeating pattern that was based on a pattern of 8 was ridiculed by modern day chemists at that point. He was told it was as arbitrary as putting them in alphabetical order, and basically the Chemical Society basically disregarded his theory. Basically his law of octaves failed beyond calcium at that current time in the known elements. Let's see here. Then you get to Mendeleev. Basically he, in 1869, is considered to be the father of the modern periodic table. He's given the most credit. Basically what he did is he grouped the elements according to increasing atomic mass from left to right in the periodic table. So from left to right, they were grouped by increasing atomic mass, and then vertically, they were grouped into columns based on similar chemical and physical properties. At the same time, Mayer published his own periodic table, also by increasing atomic mass. If you look here, these are elements that were known to pre-1700, according to where they sit in the periodic table. Then between 1700 and 1799, they were adding different elements. And then Mendeleev and Mayer arranged their elements in increasing atomic mass. So they basically had the same order. Both also left vacant spots where unknown elements should fit based on the chemical and physical properties. So the idea was these gaps that were created, they were able to actually predict what the physical and chemical properties of elements were that hadn't been discovered at that point. So Mendeleev basically published his ideas first. So the father of the modern periodic table is Mendeleev and not so much Mayer. Just has to do with when their results were published. Very similar to if you had biology, Darwin and Lord Wallace published the same idea of natural selection at very similar times. One got more credit than the other, so it's the same kind of situation with the periodic table. Mendeleev's periodic table became available 1869 before the other one appeared, so hence he gets the credit. Basically, they talked about atomic weight of an element. They corrected atomic masses of some of the known elements based on the idea that it had to go in order from left to right on the periodic table. He was so confident in his table that he was able to predict physical and chemical properties of elements that were not known at that time period. After the discovery of the elements, predictions, these are the elements that he predicted, and they were amazingly close to the actual values. So people started to see, because he had left gaps in his original table, and then you see these elements were discovered, and the way Mendeleev had laid out his table, it was a good predictor of those elements and their properties. Basically, problems started to arise because if you look at the periodic table, there are gaps or not gaps, but there's places where they flip. The atomic weights do not go in a nice, neat order from left to right, increasing from the left side to the right side. So as they had more accurate atomic weights, there was issues. If you look at a modern periodic table and you look just by mass, if you look at argon and potassium, the masses don't go in order. If you look at these other elements, cobalt and nickel, same thing. Tellurium and iodine, same thing. So there are issues as far as the modern periodic table, the weights going from left to right. Then you have another homeboy come on the scene, Moseley. Moseley basically figured out that the atomic number of the elements is really what was responsible. If you actually sequence the elements from left to right using the atomic number, the periodic table worked better. So if you basically took the atomic number from the left side of the periodic table to the right side, the properties or the fundamental qualities he talked about, physical and chemical properties, increase in regular steps. So basically, that's the key. And if you look at the modern day periodic table as it exists now, it's in order. It's arranged in order from left to right by atomic number, and it is arranged vertically by chemical and physical properties. If you look here, that's just a little history. In World War I, Gallipoli, I believe he passed away. Seaborg basically moved 14 elements. If you look at the modern day periodic table, if you look, basically these original elements here, the rare earth elements, were basically pulled down. They used to sit about right here in the periodic table. He pulled them out and rearranged the periodic table. He was the only person that actually had an element named after him while he was living. And the other thing you need to know, that's a little bit of the history. So basically the periodic table has been arranged by chemical and physical properties. They had the right idea, or were on the right track in the early stages, but as more and more discoveries became available, more accurate atomic mass, the idea of the atomic number, the way at which the table was laid out reached its current form. You do have to be aware of the current form and the format of the periodic table. If you look right here, these are called periods. So for example, this is the first period, second period, third period, fourth period. So horizontal rows are called periods. Vertical columns of the periodic table are called either groups or families. If you look, elements in any one of these groups, a vertical group like this, have similar chemical and physical properties. That's due to the fact that they have the same number of valence electrons, which we'll deal with in a later chapter, which is basically the electrons in the outside energy shell or the outside energy level. If you look right here, this is the layout of the modern periodic table. You see the rare earth elements pulled out right there. Elements in groups 1A, 7A, and 8A are called representative elements. Basically, this section of the periodic table right here, this whole section is representative. The one reason they're called representative elements is because you can actually tell from their position in the periodic table the number of valence electrons. There is another numbering system that's used now that starts here from 1. I guess it's not going to work for me. 1 right here, 2, and then this goes 3, 4, all the way 5, 6, all the way ending in 18. This is the old numbering system, and now the new numbering system, if you look, 10, 11, 12, this is 13, 14, 15, 16, and 17. All right? Let's see here. Those are group B elements. But if you look right here, the major division, or the 3 categories of elements in the periodic table, obviously the largest group is the metals. If you look at what I call the haunted staircase in the periodic table, when you look at your periodic table, the staircase is drawn in. The haunted staircase, on this side of the haunted staircase, these are all metals. On the other side, you have nonmetals, which are coded green. Finally, the ones that sit directly on the staircase are classified as metalloids. So you're supposed to, as a chemistry student, be able to look at the periodic table and tell whether something's a metal, a nonmetal, or a metalloid. Periodic law basically states that if you arrange them by increasing atomic number, which is the way the periodic table is arranged now, there is a periodic pattern in which basically the physical and chemical properties repeat. That's what periodic means, a repeating pattern. Alkali metals are the first group in the periodic table. Next group is alkaline earth metals. You have the transitional metals listed there. You have intertransitional metals, or the rare earth elements. halogens there, and then finally noble gases. These are groups that you're expected to know based on their location in the periodic table. You'll have a coloring assignment where you'll need to color these in. They all have, just keep in mind, they all have similar chemical and physical properties. So really, if you look at the periodic table, a couple things you should have learned from this. One is early ideas on how it was supposed to be arranged based on really all chemical and physical properties, grouping them together. As more and more became known about the elements, they were grouped better and better. And then the modern periodic table structure, which is as you go from left to right in the periodic table, it's arranged by atomic number. They're broken down into groups vertically in columns by chemical and physical properties.